So, welcome everybody. This is Beyond Fairness, a socio-technical view of machine learning, right? And that's me, but everyone calls me Bob, and I invite you to do so as well. Today, introduction to the course, standard approaches to fairness and the cost of fairness. That's what we're going to cover. I do record the lectures, as I said, so if you say something particularly stupid, it will be recorded here. Same goes for me. What's our problem? So there was a famous article written in a newspaper a few years ago, 7 years ago now, and you can read the subtext here. Machine bias, there's software used across the country to predict future criminals, and it's biased against blacks. And this set off a huge wave of research in machine learning to try and understand this apparent problem and to try and find mitigations for it. And that's what we're interested in this course. So the detailed agenda for today, there'll be a little bit of meta stuff, just talking about the course. I'll explain the goal of the course in a single slide, a little bit about the logistics of it, and the overall narrative arc of the course. And then we'll get into some technical content, introducing fairness, a couple of classical approaches, the idea of perfect versus approximate fairness, impossibility results, and some trade-offs. So that's what we're doing today. So what's the problem that we're interested in? So machine learning is becoming pervasive and is being used to make consequential decisions affecting people. And there's many different ethical harms that can arise. It's quite complicated. One of these is fairness, whereby the outcomes are affected by factors that are deemed inappropriate. Note my choice of words here, deemed. It's deemed by someone, right? And we'll come back to this issue of who does the deeming, whose choice are we imposing when we impose some notion of fairness. And our job as technologists is, well, what do we actually do, right? So you're technologists in training or certainly interested in technology, and so, these problems arise. What, if anything, can be done from a technological perspective? Doesn't mean that the technology solves the problem. Again, I'm choosing my words carefully. What do you do in this case? Anyway, we'll gradually get precise as we go along, but your first piece of homework is to actually just immerse yourself a little bit in the rhetoric that you'll find on the web very easily. So if you just search for fair machine learning or the ethics of AI, you'll see a ton of stuff, tons and tons of stuff. You don't have to read it all. Just sample a little bit of it, right? My objective is that you get confused and baffled, right? You should, because it is a complicated problem. I'm not going to try and catalogue all of those views. It's just an overwhelming thing. We'll zero in on one particular thing that allows us to get some insight. So what's my goal in this course? In one sentence, I kind of cheated because it's a long sentence, to introduce you to the cognitive tools, keyword, tools to think about that can help deal with the manifold problems of fairness and ethics in machine learning, particularly by viewing machine learning more broadly as a technology and even more broadly as a socio-technical system. We start narrow. In a few slides' time, we'll dive into some maths and look at very concrete ways of formulating this problem, as you would find in a typical machine learning conference. But then we'll widen our view, and we'll see that the maths, whilst important and indeed essential, isn't the whole problem. And of course, machine learning is mathematics reduced to code. And so to deal with these ethical and social problems, we do need to bridge the world of mathematics and ethics. That's what makes the topic interesting. They seem a long way apart. In many people's eyes, they are a long way apart. In some people's eyes, they're so far apart that there's a chasm that you should never cross. The idea of mathematizing ethics is anathema to some people. Anyway, this does mean that we'll need some tricky maths, but we'll also need some tricky philosophizing about what the maths means. My job, as I view it in this course, is not to present all the answers. In fact, I hardly give you any answers. I'm wanting you to get confused and baffled at a higher level than you are now. More sophisticated confusion. And I'm trying to show you some interesting and different ways of thinking about a set of problems that hardly at all solved well yet. So a few meta points to keep in mind, and this will recur during the course. I've already used the word and I stress the point. Machine learning is a technology. It's not some I mean, yes, it's new, but then again, it's not. It goes back to the 1950s. It's sold as completely unforeseen, unprecedented. The world's never seen a new technology like this. The funny thing is, if you look at historical books, that was said about lots of technologies. The railroad, right? The motor car, electricity. So we've been here before in a way, and one of my premises is that we can learn from that. Another key point, Melvin Kranzberg founded an organization called the Society for the History of Technology, and he was its president, and he wrote an article as president, and he formulated this law. Technologies are neither good nor bad, neither are they neutral. It's a little subtle. The key thing is that a technology itself, the actual object, the artifact itself, doesn't cause harm. It's when a person uses it to do something, right? If the computer's just sitting there, it's not doing anything. If I use it to process data about you, which then gets acted upon, then the harm can occur. Keeping track of when the harm occurs and under whose agency it occurs is important. Anyway, the key thing is that all technologies bring benefits and harms, which, the subtlety, are unevenly distributed between people, which is what makes the problem so tricky. We will directly grapple with the issue shortly that suppose you introduce a new technology, which on average benefits people, but for some people, it harms them a lot. How do we think about that? How do we deal with that? So my goal is to neither demonize or valorize the technology of machine learning. It's clearly very useful. It clearly causes harm, right? So we're not trying to choose which is which. We're trying to understand that so we can mitigate the harms and maximize the benefits. So to do that, we have to study it quite deeply and from multiple perspectives. So I'm going to focus on the fundamentals. And there's no point building fancy superstructures, the world's greatest piece of software, if you don't know what the ground is that you're building upon. Also, I know in the university jargon, this is a course. The word course is used for, I think, of a ponderous meal at a restaurant that goes on forever. There's the appetizer, the entree, and so on. This is more like a tapas bar, right? If you want a metaphor, right, there's lots of things to choose from. I'm not saying you have to look at all of them equally well. You might not like the fish, right? And it's not textbook knowledge. There is now a textbook, which I'll refer to shortly on this, but there's no way which you could claim that there's like a codified set of knowledge. For example, like Matthias's convex optimization course. That's pretty solidified. This is knowledge in the making, so it's rather uncertain. So the fact that there's no canonical text that I can rely upon might seem to be a bug. I'll view it as a feature, and we'll talk about that shortly. I'll indeed share many resources for you to read so you can build your own understanding of the field. And the reading is a large part of the work in doing this course. You don't have to program anything in this course, 0 lines of code, right? And any courses that have you write software, if you went along to the Friday afternoon thing last week, there was some apologies by some people. Oh, you have to program robots. This will take a long time, right? Code always takes longer than you thought. All that time that you're not spending on code, you can spend on the reading, okay? So it's fair, isn't it? So it's a newish topic, and my model here is, so there's this institution in France you may have heard of called the College of France, and it's very specifically set up so that the professors, their goal, if you're fortunate to get a job there, you're told each year give a course of lectures on what you're working on, right? Not the old stuff, the current stuff, what you're currently working on, and it's open to all people. You can look it up in Wikipedia if you want. But that's more the style of course that I'm giving here. To that end, I am going to talk about some things that I have worked on quite recently, some of them very recently. So you'll see what is the cutting edge. Cutting edge doesn't necessarily mean great, it means cutting edge, right? The content is a mixture of the technical, that is mathematical. We all see theorems, there'll be slides full of maths, and also broader stuff, conceptual, philosophical ones. I'll show you the map of this shortly. And both are equally important, all right? So don't get the mistaken impression that, oh, it's only the maths that matter, or it's only the philosophical blah, blah, blah that matters. Both matter, and the interesting thing is to understand how they fit together. Hopefully there's something difficult and challenging for everyone. So, it is, you might call it an interdisciplinary course. There's lots of versions of that. Cross-disciplinary, multidisciplinary, or transdisciplinary. I like this phrase, anti-disciplinary, right? It's like, multidisciplinary with a bad attitude, right? You deny the existence of disciplines. And why is that? Because we're interested in the problems, we follow our nose, we follow the problem. We're not going to restrict ourselves to just, we think we're computer scientists or machine learning people. We'll be looking at anthropology, psychology, sociology, politics, philosophy, as well as the maths and computing. Okay. We'll be discussing ethical viewpoints in this course. And so like things like beauty or taste in food, these are essentially, the technical jargon is an essentially contested concept. There's lots of things like, what's a beautiful face look like, or what's the best car, or just like lots of things in life. You and your friends don't necessarily agree. You have to agree to disagree. My job here is not to tell you this is the right way to think about things. I'm not going to go and tell you everybody should get the same income, or we should have a flat income tax rate, or any ethical precept like that. We're going to work on a meta level to try and understand what are the implications of such a supposition to the practice of machine learning. And so more specifically, our goal is not to solve the problem of what fairness really is. So you will find, if you do the Google search I suggested earlier on, it's a natural thing that people will try and do to say, oh, let me just get to the essence of what's really fair. You think this, you have your own definition of fairness, you have your own definition of fairness. We try and synthesize them and get to the one true meaning of fairness. I would maintain there is no one true meaning of fairness, right? Just because it's a short four-letter word doesn't mean it's got a single simple meaning. So there's no single answer, there's no one right way. So we look for a proliferation of ways of pursuing this. There's two chairs here. There's also no view from nowhere. So you might not have heard this phrase, but you've probably heard the notion of having a biased view, right? Oh, you say that, but then you're biased. And the implication of this is that there is a way of viewing a problem that's not biased, that's got no preconceptions, that doesn't carry the baggage that you're German or Australian or you're old or you're young or anything like that. There's like a purely objective way. I don't buy that, all right? And in any case, it doesn't help us, but do keep that in mind. I will try to give you some examples that are confronting. This stuff matters. It's not just an academic exercise. The choices that algorithm designers make affects the lives of people. You can go to jail or not according to what the algorithm does, right? It matters. So we want to look at these confronting examples, but we want to look at them in an analytical, calm kind of way. So we want to be a bit like Buddhists, right? We don't want to get upset about it, right? We want to be detached, but we want to be passionately committed to, solve the problem. One interesting aspect of our problem is that we can compare what machines do to people. And some folks have started to study the question, they've gone meta on this and asked, how is it that individuals will judge the behaviour of another person versus how they judge the behaviour of a computer? Because you're often comparing them. And the interesting empirical evidence is they judge them differently. You tend to judge technology by its performance and people by their intent. Now there's a big problem with that because it presumes that you know their intent, right? So there's a thing called the transparency illusion where you tend to think that just by looking at someone's behaviour, you know what's really going on inside their head. And then you judge them based on the model of that. Anyway, the point is that when we go and make comparisons about fair decision making between people and computers, we're already going uphill because we're not doing a fair comparison, right? So it's tricky. And I've said all of that. So we'll try and be as fair as possible and relaxed about criticism of our approaches. So chill. So that title, right? Let's just deconstruct the title. Beyond, right? We're looking forward, not backwards. It's an open frontier, unsettled knowledge. I already said that. Fairness is our anchor. We will, in I think lecture 6 or 7, we'll actually look at a little bit about the etymology of it and find out that it's not actually a human universal. Let me talk about It's not the, that's the key thing. It's there's many other ways that you could do this. As socio-technical, the key thing here is the hyphen, right? Gluing the two together, that's the interesting thing. Society and technology together, that's what makes our topic interesting. It's a socio-technical view. As I said before, it's not a view from nowhere, it's a particular view from some vantage point up here. And machine learning, well, we all know what that is, right? Well, we'll see. That's the meta stuff, concrete things about the course, assessment, etc. Assessment. So what's the point of assessment? It's the operationalization of epistemology. You've got to get used to these big words when you sort of dabble in philosophy. So here's the first question for you. Why do we have assessment? You take it for granted that you go to a course, of course there's assessment. Let's just think about that. In this course, I want us to think about things that we take for granted a lot. Here's the first exercise. We might have assessment as an aid to learning. I certainly will get more of your attention if you think that, you know, what you write might somehow be assessed and have some consequence in the future. Often it can be a certification of memorization or competence. That's what, you know, you get a fancy certificate with a stamp on it. It could be a motivational tool, right? To you, not me, forcing you to do the work required to learn, and I'm sure there's an element to that. Or it could be an arcane, unexamined ritual. We just do this. Of course there's exams. Of course you go and do all of this stuff all of the time. Or, more depressingly, a league table for you to prove your worth. To who? To yourself or to what? You know, oh, you got an A. Good for you. Right? So, there's some choices there, right? Some of you might think, you know, some of these are more important than others. We can talk about that in the tutorial if you want. But let me tell you my view. Since I'm in charge, my view has some weight. So I'm an epistemological fallibist. I'm certain that I'm not certain about anything, right? I've been wrong so many times in the past, it's likely I'll be wrong again. So it's therefore unreasonable that I ask you to memorize stuff which could well end up being wrong. An aid to learning is more valuable than certification, that's for sure. I think less is more, so a smaller number of larger items designed in a manner that cheating can't really help you. I like working in groups myself and figure that it's a lot of fun, and I think that way you can learn to do more, and it means that you can do kind of less individual work, as it were. I like the idea of offering freedom of choice, so you're already quite a diverse group of people from what I can figure out, the degrees that you're doing, just looking at you, where you've come from, all sorts of different diversity there, and you're all going to find different parts of the course differently interesting. Some people get terribly interested in the maths, others will find that the most tedious part of the course. So can I offer you a way to have some choice? And so indeed I can, and that's my proposed assessment, which is on the Moodle page. The Moodle page is the canonical reference for everything. So anything I say in class is an elucidation of that, but that's in writing and that's what I commit to. So the details are up there. So in essence, the main assessment item is a group essay. It's a term paper, right? It's a significant piece of work. It's not just like a couple of pages. We're talking the order of 20 pages or so, deeply researched on a particular topic arising in the course. And we'll help you get there. First, we'll do a practice essay, which isn't worth very much. And if you bomb out on it, the marks can be redeemed on the final one. It's just a practice, right? So no stress. And then we'll negotiate the topic with you, right? So you'll have an idea, I'll discuss it with you, help you frame it. Typically students overreach and try and solve the world. We narrow that down. And then as you go, you can chat about it, right? So it's kind of more closer to joint research than individual assessment. But in the end, I'll judge the quality of the written essay according to criteria that I will put up. They're not up there yet, right? All of this doesn't happen for a little while yet, so we'll be able to talk about this in the tutorial. Final logistics slide. The lecture's recorded, so you can view it if you miss it, and the weekly tutorial slot here. I know there's at least one student that this doesn't work for. We'll find out how many of you it doesn't work for, and I'll find a solution to that. And there's a few points there which I'll let you just read. Yep. So, my philosophy of teaching, we're almost done with the meta stuff. You're master's students, you're not school kids. You're responsible for your learning. You want to learn, you don't want to just pass the course. My job is to help you, right? So I don't like the verb teach, I like the verb help to learn, right? That's my job here. And I'm only going to say this once. The most important attribute that a scholar has is their intellectual integrity, right? If you're fooling yourself, there's nothing left, right? Scholars are pursuing truth. You're trying to understand how the world works. If you want to use a statistical machine learning program to write your assignment, I feel sorry for you, but not much. I'm not going to say that again. Right, so now we get onto the content. So I now want to talk about the overall narrative arc of the course. It's a hero's journey. You know, there's a literature on this about the way stories are written. Joseph Campbell wrote a very famous book on this called The Hero's Journey that George Lucas read and used it as a blueprint for the Star Wars series. Really. So I'm using it here too. There's no Jedi Knights or lightsabers. So there's essentially 3 parts to the course. First 4 lectures I would characterize as, say, the canonical received view of the problem, made as simple as I can in order to get to some of the core issues. So the stuff we do today, standard approaches to fairness. Next week, a different approach to fairness using aggregation functionals. We'll talk about some of the difficulties in choosing the fairness measure, and we'll look at another candidate notion called individual fairness and the relation of that to questions of privacy. These are all fairly mathematical. I think today's and next week's lectures are the most mathematical in terms of formulas per lecture. Right, I said that there. And then the middle part of the course, which is a bit longer, is essentially tearing all of that down. So we do all of this in the first 4 lectures. We say, look, these are all pretty good solutions. It all works. You can calculate stuff. You can prove theorems about it. But then I want to examine what's missing, right? What's the blind spots of those approaches? For example, they all rely upon defining fairness in terms of a conditional independence requirement. What does that presume? So we'll get to that. So you see there's 6 lectures in the middle, including a whole lecture on data, right? You wonder how I can give a whole lecture on data. You'll see. The categorical imperative is a whole lecture on labels, right? You have labeled data, right? Where do the labels come from? What's the significance of that? So that's maths light. There's hardly any formulas, but I think it's just as challenging. Sebastian is sitting at the back, is one of your tutors, will give a guest lecture. He's got a background in political philosophy, and he will give a lecture tentatively titled Policy, Power and Politics. It's another dimension to the ethics of machine learning. And then the final, the resolution, right? I mean, you know, a good movie, there's got to be an ending. There's got to be a resolution, right? Luke's got to do what Luke's got to do. And so that's what these are about, right? So standard problem, all of the difficulties with the standard problem, and then what might one do about it. Okay. Okay, so that's all the meta stuff done. Let's dive into it. Just a typographical convention in my slides. This lurid pink color I use sparingly as a signal that this is something that you should do. Like specific readings that I give you where I say, you should look at this. There's lots of other references that I give you where you can look at it if you want to. Pink means Bob's asking me to at least have a go at doing it, right? So these are The first and the third are kind of overviews of this topic. The first one is the best single source you'd find. It's a textbook, right? The FairML textbook, you can just download it. A lot of what we cover is in there, but not everything by any means, and there's certainly some stuff in that book that we don't cover, but there's a good overlap. This middle one, this paper that I co-authored a few years ago, is the essentially what I'm going to talk about in the rest of today's lecture. And Sebastian pointed me to the first two chapters of Peter Singer's book on practical ethics. If you've never tried to read any formal literature on ethics, like philosophy of ethics, this is a good place to start, right? It's relatively short, it's not fancy and technical, and it is grounded in practical decision making. And he presents a compelling argument why you do need a bit of formalized thinking about ethics in order to make practical decisions. So I think that's a good bit of homework to have a look at. And all of these things that I point to are in the resources section for each lecture on the Moodle site. So what's the simplest way of describing a fair machine learning problem? So, I'm presuming you're all quite familiar with the basic notion of making a binary classifier, and we have some features about some people, and we want to go and make a prediction about how well they'll do. Maybe we ingest their CVs, right? We turn that into numbers, and we try and make a prediction of how well they'll do on a job. And so we're trying to predict, whether they'll be good or bad at something. It doesn't matter what that is, we've just abstracted that. So that's a standard machine learning problem. There's arguably, in the way that I described it, no particular ethical concerns that you might have there. But where it gets more interesting is that if there are certain features about your instances that you might choose to not want to discriminate on the basis of, right? Now, it is a choice. One of the most salient ones that's talked about a lot would be the sex of the person. Suppose you built this machine, a recruiting tool, like Amazon did, to try and predict who would be good in a particular job. And suppose it turned out that it ended up predicting that men were going to be better in the job than women more often than you would have liked. I'm being slightly cagey in my language here, but that's essentially the motivating example. Now, whether it's men versus women or black versus white, mathematically that doesn't matter. But that's where the ethical conundrum comes in, right? So how do we understand these machine learning algorithms? So I said earlier, there's no programming in this course, but it's even better. There's not even any algorithms, right? And I can avoid algorithms by a simple trick, by only reasoning with the optimal thing to do. So we can do that mathematically. Algorithms, after all, are just a function, right? So we're working with maths, and you do know that computer programs are just mathematical proofs. You know this, right? The Curry-Howard isomorphism. So therefore, there's nothing special about programs. We're just going to work with functions and the abstract view of things. And it goes back a long way. Like I said, machine learning is not that new. Abraham Wald developed statistical decision theory in 1948. And the idea in this binary classification problem is that you'll have these two class conditional distributions, hopefully familiar with this terminology. That might be, the distribution of your feature for people that are not good at the job, the distribution of the feature that are good at the job. And then the idea is your classifier in this case is to just, you've only got a single real valued feature, you pick a threshold, and then you predict that any new instance with a feature above that threshold is going to be good. Right? I hope you've seen this story before. If not, we can talk about it in the tutorial. And then from that, you can work out the probability that your classifier gets it wrong, right? And that's going to be related to the area of the overlap here. And it's going to depend upon where you put the threshold. So hopefully you're kind of familiar with that. Now, this is a cartoon version. In practice, our feature vector is very high dimensional, and therefore our choice is not just a single number, it's a complicated decision boundary. And we might not just have two classes, we might have k classes. But I've reduced it to the simplest version here because we want to introduce this new complication of fairness. Let's at least start with the simplest problem. We'll see that even this simplest problem, binary classification, once you introduce the additional constraint of fairness, becomes a lot more difficult. In general, the minimal risk is not zero. So these statistical decision problems, often you can't predict perfectly, right? That would happen here because there's an overlap on the basis of the measurements that you make. Like if you just look at someone's CV, can you predict that they're going to do well in a job? No. Is there some signal there that gives you some guidance? Yes. That's the canonical situation that we're in machine learning, right? There is some signal, but it's not perfect. Anyway, the key point about this is that when you set it up this way and you posit, you have to make this presumption that we know the distribution of the data, then you can analytically work out what the optimal decision is. So you'll see this, there's lots of standard, theory of machine learning textbooks that would have this in chapter 1. And in this particular case, it's extremely simple. The optimal classifier you can prove will be of this form. Now, I just said it before, but it's actually a theorem that you can prove. And this notation, we'll use it a little, several times in the course if you haven't seen before. This is the Iverson bracket. So it just means if you see that double square bracket and there's a proposition inside it, and the proposition is true, you get the value 1, otherwise you get the value 0. It's just a compact way of, instead of saying if blah, 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 then 1, if blah, 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 then 0. Okay, it's quite standard. Anyway, that is the optimal classifier, right? So you might think, well, if it's that easy, on one slide you can just write down the optimal classifier. Why do we bother with all of the learning algorithms and all of that pain? The point is that you don't have access to this distribution, right? Let that sink in. All you actually get in practice is a bunch of samples. So we've now got to be thinking at two different levels. We've got to keep in mind what you actually do, right? You measure some data, you have to program the computer. Yes, all of that is necessary. But for the sake of understanding the choices about how we might deal with fairness, we can kind of sweep all that under the carpet by saying, suppose we were in this nicer situation where we had infinite data. Now, having infinite data allows you, and infinite compute, we can get an arbitrarily good estimate of that probability distribution. So why don't we just presume that we can do that? It's an idealization, right? I understand it's an idealization, and any conclusion that you draw from this idealization, you will then have to think, well, what will that mean if we want to actually go and do it in practice? And we'll see that. But for now, for the rest of the lecture, we're going to assume the idealization. We'll do lots of work in that ideal world. And at the very end, I'll say, oh, look, actually, it's pretty easy to pop back down to finite samples. But the beauty of working in the abstract view is that we derive some insight. We will be able to see what the optimal fairness-aware classifier looks like and what the trade-offs are. Right, I already said this, like where's the learning algorithm, where's the model? There's no learning algorithm because there's no data, right? We've already abstracted that into the probability distribution. There's no model class. Where's the neural network, right? There's no model class here because we've worked out the optimal hypothesis. In principle, if you wanted to, you could say we've done a search over all measurable functions. So our model class is everything, and we've chosen the single best one. But I don't even need to talk about all of those that I didn't choose because I can just work with the optimal one. Right, and if the problem is difficult and throws up hairy issues in this abstract view, then it's going to be even harder when we do it with finite samples. So let's introduce a simple fairness constraint. So remember, in the back of your mind, today we're just playing with a binary classification problem, but now we're going to add to it the complication of some notion of fairness. So how do we think about that? So what we're introducing now is the simplest version of what is called group fairness. In lecture 3 or 4, we will meet a thing called individual fairness. So as before, we think we have a feature, x, viewed as a random variable. So just think of that as a vector. It might be a vector of attributes about a person, their test results, their age, address, name, all sorts of things. So in my slides, things in this sans serif font are random variables, sets in uppercase Roman, and probability measures are written like this. We assume we've got a label. It's a binary label, and so we'll just conventionally use that as either 0 or 1, and that might be the thing that we're trying to predict, right? Whether they're going to default on a loan. These systems are used, right? Now, right? When your bank's deciding whether to lend you some money, they will use a statistical model to predict what's the likelihood of you actually paying back the loan, and on the basis of that, give you the loan or not. We have a sensitive attribute, right? So this is different to the label. So Y is whether or not you're going to default on the loan. S is the sensitive attribute, right? So something emotionally charged, perhaps, ethically charged, your sex or your race or the postcode where you live, right? All of the things that people feel uncomfortable if they get used in making a consequential decision. The length of your hair, right? It shouldn't matter, right? If I say, you're out of here because your hair's too long, right? They're sensitive, and so we use the letter S for that. And remember, I use this abusive notation like almost every machine learning paper you'll ever find. Of course, what I really mean, it's a random variable, right? So there's some sample space and it's a measurable function. But I presume you understand what random variables are, so that's what these things are. And to start with, again, we make life as simple as possible, and we'll assume our sensitive attribute is just binary. Again, we can complicate it, and boy, it gets a lot more complicated when we do. But so this could simply be, let's say, sex, right? Male or female. So you've got two things, whether or not you're going to get the loan or not, and what your sex is. And we're going to learn from a stack of historical data and use that to make a prediction about your likelihood of defaulting on the loan. And as per usual in most machine learning papers, we assume that our data is actually a sequence of IID samples of these random variables, right? So that's what we're going to assume we actually get, and we can have as many of them as we want. We're not going to worry about the finite sample effects dealing with limited data. I've already given you the interpretation on the second line. Yes, and our specific goal, we ingest all of this data, we build our model, our predictor, and then what does that black box have to do? We require them when a new X comes along, a new person walks into the bank, they look at their feature vector, they make a prediction whether they're going to default on the loan or not, and then act on that basis, right? Our prediction may well be randomized, right? Sometimes it's just technically convenient to have randomized predictions. So far, that's all quite simple. So our prediction is essentially what we're trying to do is it's like a regression problem. We're trying to predict the Y given the value of X, right? So classic regression is we just take the expected value of that. Our Y's are just binary, right? So we can presume that our prediction is actually a Bernoulli prediction. It's a randomized prediction, right? So this just makes it mathematically easier to proceed. So the notation here is simply that we've got a Bernoulli distribution, so that's a biased coin with probability of a 1 being P. And then we have this conditional distribution where F is our predictor, right? So actually F, that should be, I don't have a pointer. This is the interval 0, 1. Sorry, I just noticed that. Okay, that's all standard, right? Here's something new. These, what I'm introducing now, are arguably the two simplest vanilla versions of fairness for this problem. right? We've got a binary classification problem with a binary sensitive attribute, and now we go and ask ourselves, how can we make the problem fair? So one way we can go and do that is we can demand this. This has got a name, right? The names don't really mean anything, right? There's a long literature why they're called that, all sorts of historical reasons. It doesn't really matter. They're just names for these formulas, okay? It's the formula that matters. And look at what this says here. This says that the probability of predicting of your classifier, y hat, being equal to 1 is the same regardless of whether s equals 0 or s equals 1, right? So this is reasonable, right? This is saying the probability that you say, yes, they should get a loan should not depend upon their sex. That's what that says. Or you could say, you think, well, we're done, right? End of course. It's that simple. But no, the reason it gets more complicated is that then someone else will come along and say, well, hang on a sec, I think this is a better way of encoding what we mean by fairness. And have a look what this says. So here we rely upon the true label. So now we go and posit that we make a prediction about a person and we actually go and check whether or not they do default upon the loan, and we are interested in comparing essentially whether we're making an error, right? So if this wasn't here, this is essentially asking that our classifier was correct, right? We predicted they would not default, and lo and behold, they did not default. Good job. We demand that the probability of getting it correct doesn't depend upon their sex. Both of those sound completely reasonable, but they're different. Both of them are a stipulation of perfection, right? There's an equality sign here, right? It's exactly the same according to whether you're man or woman. They are couched in terms of conditional probabilities, which we could, in principle, compute if we had full access to the joint probability distribution. But there's two of them. Yep.
Could you explain why in this formalism the sensitive attribute is not part of the inputs to the algorithm?
We'll get to that, and I didn't say that it wasn't. So, but this is it's a good question. I'll answer now. So, in the way we think about this, so one of the first approaches people thought of was to say, well, surely if we simply don't let the algorithm know the person's sex, we're all good to go, right? Just feed in their CV and we're all fine. And you go and have lots of data. But guess what? People with names who's Jane or Susan or Mary tend to be women. If it's John, Bill or Bob, it's Bob. It's male, right? So that issue where merely screening off the sensitive attribute, it doesn't work. So the paper, one of the foundational papers written by Moritz Hart and Cynthia Dwork that I cite either in this lecture or another one is called Fairness Through Awareness. It's a jokey kind of title, but the point is they spell out this argument that merely not looking at the sensitive attribute doesn't work when you've got a sufficiently powerful predictor because it can go and work out the sensitive feature in the first place. If you want to be able to certify that your algorithm is fair, let's presume that the predictor is all-powerful. To that end, we might as well give it the S and then demand that it behaves nicely in that case. That's what we're going to do. But we will see later on in the lecture, when I look at the optimal solution for this problem, you can state it in either way. Anyway, there's lots of other measures, right? You can look up with all sorts of different funny names, and I reiterate, going from the name to the formula, there's no logic to that, and I never remember the names, right? I've worked on this, I've written papers on it, I still forget the names, right? I'll probably do it in front of you. Interesting exercise, right? Just take these two and try and write out in words the ethical principle that they encode, right? I mean, you all accept that demanding this is not the same as demanding that, in general, right? I mean, for certain distributions, they'll coincide, right? So straight away, we have our first ethical choice. Which of these is fairer? Right? There's no answer to that question. It is a question that doesn't work. But what you can try and do is you can try and say, if I'm demanding this or I'm demanding that, here's what I'm doing. So try and put that into words. There's an example of someone trying to do this, a whole paper where they looked at a particular measure of fairness, where they had a go at doing this. So a couple of observations already. Oh, yes, I've already said this, right? We have a choice, which of these is really fair or right? Bad question, right? I'm not going to answer that. Instead, I'm going to make the question harder, because what I've offered there are definitions of perfection. So, hands up anyone who's ever done anything in their life perfectly. Yeah, right. So this is engineering, right? You can't do it perfectly. So this is not satisfactory, right? You know, it's silly to demand perfection. We know that there's lots of things wrong in the world. We would be very happy if things are pretty damn good, right? So we need measures of how pretty damn good they are. Now, unfortunately, we've got more choices to make. There's many ways that you could go and do that. Here's a couple that I've written down, right? I memorized it before walking in here, but I've already forgotten. This stands for disparate impact, and I've forgotten what this stands for already, right? But it doesn't matter because it's just a symbol, right? I can't remember the words that are used, but they're obvious ones, right? I mean, let's take this one. It's nice and simple. Perfection demanded that equaled that. So let's just measure the difference. And if it's close to 0, we say it's pretty good, and if it's a long way apart. Or equivalently, we could have said make the ratio equal to 1. So, these have certain natural ranges. You get perfect fairness when that or that occurs. So we've now got some way of kind of measuring fairness, remembering that it's, we've made some choices here. Now, there's a subtlety to this, which I'm not going to talk about right now. It's just on this slide. You can work through this. It's really only manifests itself later on, so I'll leave you to look at that in your own time, and that as well, because I want to stick to time, and it's now 3 o'clock and we have a 5-minute break. Hi.
General question about the course. If it makes sense for me to take it.
Don't stand here because you'll get recorded. So, I guess and so what I'm doing here is some so what I just went through, right? So right. So I guess it's hard for me to say. Was it to give it a go? There's no plan that you it's logically possible that The more philosophical things and what makes a good philosopher, right? No, you write it in a group. Yes, so I mandate that you're in a group between 2 and 4 people. So I'm really looking at doing it on your own. There is a downside in that. If you team up with some people that let you down, that's tough. But guess what? That's what happens in life. So that's part of the exercise, right? And I like the idea. I mean, I've done this before, and students with slightly different backgrounds going to meet out and doing that collectively, writing something, you submit it on the board, and then everybody gets to do it. It's more like that's what I'm after, right? I mean, if you zeroed in on a technical mathematical topic, it'll be relations. If you chose instead to look at some non-mathematical side of things, then we'll let you one of this course 2 years ago, some of the papers were full of maths, others haven't. Right? It's your choice. So I'm trying to be original. Means there's very few people in the world, right? The people with a strong quantitative struggle with so make friends with no, there's, I don't know exactly because I haven't seen those information, but maybe when we go to the tutorial, my guess is that the majority of students, but I know that some students so you're going to think Okay, we'll get going again. That was indeed 5 minutes. Right, so that was the warm-up. In the second part of the lecture, we're going to talk about how you integrate those notions of fairness, that approximate fairness, how you include that in the statement of the overall machine learning problem, and what is the significance of that. And what we'll actually do is, for this problem, which I reiterate is the simplest problem that it makes sense to talk about, a fair machine learning problem, we can actually write down a formula containing the optimal solution. It's a little daunting at first, but the key thing I want you to understand is the interpretation of it, which I will dwell on a little bit. So what I'm presenting here is the paper I did with Aditya Menon 5 years ago. It probably took us 6 months of work to do, and you're going to try and absorb it in 45 minutes. So I understand that's hard, and I'd be astonished if you follow everything, but I'm going to try and single out the key takeaway messages, but I'm envisaging you'll have to do a little bit of homework afterwards, going through it, asking questions and so on. All right. So the heading for this part is fairness as risk. What do I mean by that? Actually, just as a warm-up, before we get there, this is an important thing. More homework for you to do, impossibility results. So I introduced two different notions of fairness. I told you there's lots of them. In a single sentence, a very important point that you need to learn, and I'm pointing you to where you can go and learn this, is that you can very easily set up, here's 2 or 3 very plausible fairness definitions. Each one of them looks absolutely fine, right? But on any problem that you encounter, it is impossible to satisfy all of them simultaneously. You can be fair this way, but in so doing, you can't be fair that way. And it's a theorem, okay? It tells you that you just can't do it. So this is important. So I don't want to stress this. The proof of this, I don't find is terribly insightful. It's like, it's true, but you don't learn a lot from the proof. You do learn a lot, I think, from thinking about the result, which is why I'm not giving you the proof. I'm giving you a pointer to the best proof that I know, which is in one of my former PhD students' thesis. So that's linked here, and his thesis is available. I'm not asking you to read the whole thesis. You just dive into section 5.4. It's self-contained. It's basically redoing the Kleinberg proof, I think, more cleanly and more generally. And in particular, Daniel does it for the case of imperfect fairness. But look, the key takeaway to remember is that you introduce a small number of entirely plausible fairness measures, and straight away we've got a big difficulty because we can't satisfy all of them at once. Therefore, the choice matters. Yep, so that's what I say. This essentially contested nature of fairness. Okay, so that's some homework for you. So how do we deal with this? So that's motivation, right? So we know that it's impossible to satisfy everyone, but that's life. I've already argued that there's no point in shooting for perfection because you never get perfection in any other ways. Like even when we don't have fairness, we never make perfect predictors, right? Or almost never. There's usually some kind of error, so we have to go and deal with that. And so what is it that we're going to do? What we're going to do is we're going to look at quite generally how to transform a standard machine learning problem, which you normally formulate in terms of minimizing an expected risk. That's the expectation of a loss function. That's a standard way we do a supervised learning problem. We're going to show how to augment that risk functional in a manner that encodes these fairness constraints. The way I introduce the fairness constraints were in terms of these conditional probabilities. It's not at all obvious how you feed that into your optimizer. What I'm going to show you is that you can rewrite them in a manner that you've basically just changed your objective function. So instead of just optimizing for prediction error, you're optimizing for some combination of prediction error and fairness. Now, that high-level statement that I just said, that's the first important thing to understand. Just the fact that you can do that is already very valuable. Actually doing it is another matter, right? And that involves some technicalities. And so we have, see, here's where I'm expecting to eventually lose all of you at some point. Let's see how far we get. So we have our classifier, right? It's a map from our feature vector x to the numbers between 0 and 1. And we treat it as a randomized classifier. It's spitting out a probability. And so what that means is that if f of x equals p, it means that it predicts, the probability that it predicts y equals 1, given the value of x, is p. We have our x and y drawn from some distribution on x Cartesian product 0, 1. The symbol delta applied to a set is the set of distributions on that set, right? So it's a standard notation that I've said there. And what is it that we want? We want a risk function. This looks a little daunting, but I've just given the type signature of it, right? It's a function that eats this and gives you that, right? So it spits out a positive real number, and what is it given? It's given, it's a Cartesian product, so it's given this thing. What's this thing? This is a set of functions. This is the, if you've not seen this notation, I've got a set and I've got another set, right? Set to a set power. It's just a compact way of saying this set of functions from x to 0, 1, right? X is maybe a big vector, an n vector. So this is the set of all possible functions, right? So that's a predictor. That's what our predictor does. he eats an X and he spits out a 0, 1. I have a candidate predictor, this risk functional eats that. He also eats the joint distribution, right? So this is just a pedantic way of saying I've got a risk functional that takes a predictor and a joint distribution and gives me a positive number, right? But I'm just trying to be precise about it, right? So this is how we would use it, right? So here I've written it with its arguments. I feed it a function from x to 0, 1, and I feed it a joint distribution. And what's it supposed to do? I've just told you its type. What it's supposed to do is it's supposed to measure the risk of the predictor f when the data are jointly distributed according to D. It's telling you how good f is, right? How good f is does depend upon D. Of course it does. D is our abstraction of the data, right? And how good our machine is depends upon the predictor. So we certainly need both of them, but we don't need anything else. So many things in machine learning are well abstracted by this. It's a standard sort of thing that we do. So that's the general abstract type, right? So you have this functional R that eats an F and a D. Let's look at some particular instances, which maybe you've already seen before. So you can talk about the false negative rate or the false positive rate, right? So these two things up here, right? They're standard things that are used, but we recognize, oh, they're just risk functionals, right? They eat an F and a D and they spit out a number. They tell you how well you're doing. So if D is fixed, we can make the notation a little simpler and we can just talk about the false negative rate of the F. The false negative rate is, what's the probability that our predictor says no and is wrong, right? False positive rate is what's the probability that our predictor says yes and is wrong. Right, so these are basic risk functionals and they can be used as building blocks to make a fancier risk functional. And this is often done. You might not have seen it done this way, but it's actually under the hood of a lot of machine learning applications. So, if you think about the ethical importance of a false negative and a false positive, right, in our bank loan example. So remember, we're predicting whether or not someone will default on a loan. So a false positive would be to say, we think they would default, but they didn't. What's the ethical problem with that? Well, the ethical problem with that is that, you weren't going to default on the loan, but we've denied you the loan. You're pissed about it. False negative would be the bank incorrectly thinks that you won't default on the loan, but actually, you did. And so they lose money. Now observe, right? Here it's just maths. When you go and translate it into action, those two things apply to the two agents at hand here, right? The false positive rate is controlling how much harm is done to the customer. The false negative rate is controlling how much harm is done to the bank. How do you balance them off? Well, you can do something like this, right? It's a trade-off, right? You might say, oh, well, the false positive is really important. False negative, we don't care about so much, right? If you're a really kind-hearted bank. Or if you're really mean, you might say, we don't care about false positives, but we don't want to lose any money. Well, great, we just give you a knob, right? That's what engineers do. Take a hard problem, put a knob on it, right? So you can adjust it to the way you like it, right? It's like adjusting a thermostat. And that's what we've done here. Now, we have introduced another parameter because this is just something that you've got to carry around in the analysis. You have to talk about the prior probability of a y equals 1. This is just the prior probability that people default. 10% of people in the entire population default on the loan, or maybe it's 50%. It comes into the analysis, so we need to have a symbol for it. And this is a standard risk functionality that you can thus define. It's got two parameters. The pi is essentially given by the data. The c is a design choice that trades off those two different types of harm. Okay? And we just do the weighted sum of these. I haven't told you why I've done it this way, right? But I'm summarizing a lot of work in a short time. Anyway, this thing underpins lots of stuff in theoretical machine learning, and one way of understanding it is it's actually the expected loss on this problem for a particular loss function, namely the cost-sensitive misclassification loss. Now, if you haven't heard of that before, you have heard of a special case, which is the 0-1 loss, right? You all heard of the 0-1 loss. The 0-1 loss is you get a penalty of 1 if you make an error, right? Regardless of whether that error is a false positive or a false negative. The cost-sensitive misclassification loss gives you a knob that allows you to pay a bigger price, for example, if you make a false positive than if you make a false negative. And this matters in lots of problems. Like, regardless of fairness concerns, just think of doing medical diagnosis, right? You know, just think through the implications of false positive and false negative for a statistical diagnostic test. Anyway, this is the expected risk functional that you get when you take the average of a cost-sensitive misclassification loss with parameter C under our distribution of data with a prior pi. Right. And if you want to learn more about that way of thinking about machine learning problems from this more abstract perspective that's doing things in terms of expectations, you can look at this paper that I've shared. Carrying around pi is a pain. We can simplify things. We can say, let's assume it's equal to a half, right? So we've got, we often do this, right, where we just look at the balanced case. And so now one of the parameters disappears and we can just write this, right? So this is the balanced loss and it's just 2 times this with a half there, right? And with these objective functionals, like if I have an objective functional and then I replace it with something which is 7 times that, the scaling doesn't really matter because we're only ever interested in an argmin, right? We come up with these functionals as something to minimize. The actual number doesn't matter so much. What matters is that we've minimized it, right? So that's why, you know, I can play loose and fast with constants just to make things pretty. So in this more general setup, so I alluded to this in the first part of the lecture. So in this general setup, we've got a joint distribution, a binary classification problem. We have cost-sensitive misclassification loss with a parameter C that allows us to trade off the false positives and false negatives. Then you can work out, it's a theorem, that you can compute the Bayes optimal classifier, right, for this problem. It's the best that you can do, right? Forget about trying to come up with better performance. You don't need to go and do benchmarks. You don't need your neural network. It's exact, it's perfect. There's nothing you can do that's better. But in order to write this down, of course, I'm assuming I have access to the joint distribution, which is fine. We're doing a theoretical exercise here. And this is what it looks like. And it might look a little opaque to you, but let's just break it down. So I've just introduced this notation eta. This is just the conditional distribution that y equals 1 given the value of x, right? So, you know, if we take this value of x, this feature vector, what's the probability that y equals 1? So, you know, for our toy example, you know, if you already had lots of money in your bank account, you had a wealthy father, you've never defaulted on a loan, this is looking good, right? Probability that you will not default is very high. Anyway, so the general form looks like this. Remember the Iverson bracket notation. It's equal to 1 if the proposition inside is true, it equals 0 otherwise. So what this says is that if eta is greater than some threshold C, output 1, otherwise output 0. This business here is just a technicality, right? It doesn't really matter. You can just ignore it, and alpha is arbitrary, right? So I should have just put this in grey. This is the key thing, right? Now, observe that it depends upon C. This makes sense, right? So you've got this eta. Think what that eta means, right? It's giving you some probability here, right? There's an 80% probability that y equals 1 given this value of x. Depending upon our choice of C, right? Depending upon the way we trade off false positive and false negative, that will change whether or not we output a 1 or not. This makes sense, right? The more stringent the requirement that we get things right, for example, that we don't want to make a false positive, we want to make damn sure, right? So we'll have a higher bar. The fact that it works out so simply is very nice, right? I mean, a priori, who's to say that you could even solve this analytically? It turns out that you can. But anyway, the key point is you can work this out, right? If you haven't seen it before, dig into the literature and try and understand why it has this form, and it depends upon this value C. So I'm stressing this because what we're going to do now is we're going to say, fine, you've solved that problem, binary classification with a cost-sensitive loss, you've got the optimal solution, that's just great. Now impose a fairness constraint and then ask how the solution changes, right? Now, we would expect that the solution would change. If the solution didn't change, then we're done, right? Because that would mean that we don't have to pay any attention to the fairness constraints. But it does change, and so what we need to do now is to work out how it does change. So, in order to do that, we've got to introduce our sensitive attribute. So now it gets a little more complicated, right? That was easy, now it's complicated. So now we don't just have the X and the Y, we've also got S. And we posit that they're drawn from some big joint distribution, okay? So this notation, I don't use it very often, but just the curly L, that's just the probability law of X and S. If X and S are random variables, you stick them in a vector, they have a distribution, that's what that is. It's the distribution of X and S. So there's some notation there, I should say is a meta point. So some of the slides in the course are quite mathematical. In my experience, when you're working through presenting some formulas like this, for many people you're going too slow, for many people you're going too fast. The set of people for which I'm going the right speed is almost zero. So in many cases, I'll be suggesting to you that you read these slides afterwards. I have tried to make them self-contained, right? So in some cases I give proofs and there's no way I'm going to walk through them line by line in the slides. You can go and look at it. Since I'm never going to give you an exam to reproduce the proofs, at one level it doesn't matter, but I figured you'll be interested to figure it out. Anyway, so now we can define some other quantities where we are now repurposing this functional that we defined, right? So FNR is just a function, like it's like in programming. We've already defined this function. We can go and use that. We can call it with all sorts of different arguments. Previously, we called it with the distribution of x's and y's. But here, right, I've got dp is the probability law of x comma s, not x comma y, x comma s. We're looking at the joint distribution of the feature and the sensitive attribute. Of course I can plug that in there, right? I mean, what it exactly means is yet to be seen, but I can indeed do it. And if you plug it in, you substitute in, you find, oh, it's just this, right? And so then we can go and these two measures of approximate fairness, we can do the same thing with this joint distribution. I reiterate that this dp defined up there is the joint distribution of the x's and the s's. Where am I heading with this? Before we introduced the s variable, we just had the x's and the y's, right? And our job, right, as the machine learning algorithm was, given the x, predict the y. Now we're looking at the x's and the s's. Now you asked before this question of, do you get access to the s or not? And I gave the example that if we know the person's name, then we can go and predict the sex, right? So develop that thought. You might think, well, maybe what underpins how hard it is to solve this fair aware learning problem is how easy is it to predict the s from the x. If I could not predict the sex of the person from the feature vector that I've got, then information theoretically that would be like not having the S in the first place. What am I doing here? I'm using functionals that we've defined that can capture how hard a learning problem is, but I'm using them to look at the learning problem of predicting S from X instead of Y from S. We'll see why in a minute. Right. So what do we do? How much of this do I need to say? Right, so I'm going to, when we have a distribution D with a bar over it, it's going to be a joint distribution of the feature vector and the sensitive feature. When there's no bar, it's going to be a joint distribution of the X and the label that we're trying to predict. Because where I'm going to get to, maybe we work backwards on this slide, where I'm going to get to is this here. This, in a way, is the key abstraction in the paper that I'm summarizing. And in words, what does it say? It says, if we ignore this, so clearly if I set lambda to 0, it's like this isn't here. This here, this is our risk functional, right? We can capture the quality of how well we can solve our machine learning problem. That is, F is a candidate solution, D is a distribution of the data. This term alone is our standard expected risk. It's measuring how good our learning problem is. It turns out that we can codify the fairness-aware machine learning problem by taking that and augmenting it with a second term. And this second term looks at the effective risk of a fairness problem, is what I've called it, where we've now looking at the question of predicting the sensitive attribute from the data. What we want to do is we want to do well on this and we want to do badly on that. And it turns out that that's a way of capturing the machine learning problem. We're using these building blocks. Like you've already got your algorithms that you can go and optimize. You say, here's my model class, I just feed in the data. We've already got that machinery. The logic behind what I'm presenting you is, how can I use the same theoretical machinery that allows me to look at the performance of a predictor whilst ignoring fairness? How can I use that in order to also take account of fairness? So that's what we're trying to do here. So what you end up with is, if you work through all of this, you'll end up with a new objective function that now has 3 arguments. The FA stands for fairness aware, and it takes our predictor, our candidate predictor F. It's got the joint distribution of the X's and the Y's. That's the original prediction problem. And it's got the joint distribution of the X's and the S's. That's the ethical headache that we've got. And we can take a particular version of this using our cost-sensitive loss, and we end up having more parameters. It's unfortunately, you can't really get rid of this. You choose a parameter C. You pick your cost-sensitive loss for your original problem. That's the standard one we talked about. You choose a different parameter, C bar, for the fairness-aware problem, and you've also got a trade-off parameter. So it turns out, yes, this is the key thing. So it turns out, and this is quite a lot of work to get to. Yep.
A quick question: what exactly does the lambda mean?
It's we'll get to that. We'll get to that. So for the time being, just think of it as we're trying to do 2 things here. In essence, we want to be able to predict well, and we want to be fair.
So it basically means how important it is for us to be fair.
That's right. That's right. So this is a standard move that an engineer will make, right? You have a single objective, you optimize for it. Someone comes along with another objective, you say, it's a trade-off, right? There's always trade-offs. So what do? You put a trade-off parameter in there. And then you try and solve the problem in general, and then you can go and ask, maybe the trade-off doesn't matter. If you can solve it for all lambda, and lambda doesn't really matter, then it's great. Whereas if it does matter, then you've got to pay attention to it. We'll get to that, right? It turns out that sometimes it doesn't matter at all. Sometimes it matters enormously. So we just carry along the general case.
So it basically also means, if we can solve it for all lambdas, we don't even need to try to be fair.
No, it doesn't mean that. So lambda controls how much attention you pay to the additional requirement that you have to be fair. Right? So think of it this way. You're working for the bank. First up, you try and build a really good predictor. Right? They want the predictor to be good because your profitability depends upon it. You make that as good as possible. Then there's all sorts of societal pressures that says, no, you also have to be fair. We will see that there is a trade-off. Right? It's a genuine trade-off. That is, in order, suppose you ignore all the fairness concerns. You make your predictor. You then go and measure how fair you are, and it turns out you're not very fair at all. There's newspaper reports, oh my gosh, we've got to go and do something about it. Your boss says, okay, adjust the classifier so it now becomes a bit fairer. You tell him, but I've already gone and chosen the optimal classifier. Good for you. But you chose the classifier that was optimal for the problem that ignored the fairness concern. Therefore, imposing an additional constraint can only make your performance worse. It can't make it better because you already chose the optimal one, right? And so now it comes to a trade-off. You can tell your boss, I can improve fairness by 20% at a cost of 1% to our revenue. He'll say, okay, do it. Or you could say to him, I can improve the fairness by 1% at a cost of 20% to our revenue. And he'll say, we'll spend the money on a PR firm and whitewash it, right? I don't know, right? So there's different choices that you would make.
So it's more about trying to find an optimal trade-off.
Yes, it's our job as technologists is to, do the analysis of the problem and eventually put it to people. So there are some decisions that you have to make. I gave you an example, right? If you're the manager for the bank, right, that's his problem to decide, right? And how he does that, that's not our job to tell him. But what we can tell him is that if you do this, this is what you will achieve, right? And you might say, look, you can increase the fairness enormously at a very small price. Yeah, you might as well do it, right? But the only way you can do that is to actually have all of the numbers there, right? Rather than just saying, oh, I think it would be good to be fair. You want to be able to quantify the price. If you were optimal before and you now are asked to do something better, something different, you can't be optimal. You can't presume that you're optimal anymore. Anyway, so the key point with all of this mathematical development is the claim that I've got up here. So I ended up with this risk functional with these parameters, and it turns out that this inequality holds true if and only if this inequality holds true. This was our approximate measure of fairness, right? Remember, I introduced this a number of slides ago. I started off with perfect fairness. I said you can't get perfection, so we're going to find this thing di of f that measures the difference. So it's a bit of work to do, but it turns out that this thing here can be controlled by that. This is a slightly oblique kind of result. What would have been nicer would be to show that actually this di of s is a cost-sensitive risk. What this says here is that I nevertheless can control it, right? And there's this weird nonlinear transformation that you've got to do. So if I have control of the thing on the right, that means I have some control on the thing on the left, right? Only via this inequality. I mean, that's just the way the maths worked out. So as I say, it doesn't say that DI is a cost-sensitive risk, but it does say that the DI constraint, that is demanding that DI is greater than or equal to blah, is equivalent to a CS balance constraint. It's a subtle point. If they were the same thing, then this line in white would follow trivially. It turns out this is actually all we need, so that's good, we can continue with the argument. Anyway, so there's a detailed proof in the paper about that. And this is what we get. We get alignment in terms of this inequality.
One thing about
Yep.
the slide. What would be so great if it's a cost-sensitive risk? If DI would be a cost-sensitive risk?
It turns out that these cost-sensitive risks are primitive building blocks. So for these prediction problems, you have to choose a loss function, right? And that's a significant choice. There's lots of different loss functions you can choose. The vast majority of practice in machine learning, it's kind of swept under the carpet. You just say, oh, we use this loss that everybody else uses. But if we're now trying to pay attention to the consequences on people, it seems reasonable that you have some kind of justification for it. So think of the example I gave with the false positive and false negative with the medical diagnosis. There it's got a clear interpretation, right? Here, we're just looking at a classification problem. The objective of the black box is to predict a label. It's either this or it's that. Oftentimes, you actually try and solve a more complicated problem, which is called class probability estimation. So, the classic example is the weather, right? I, as the weatherman, can either say it will rain tomorrow or it won't rain tomorrow. Right? I could do that. What is done nowadays is I say there's a 70% chance that it will rain tomorrow. The logic is this is more useful information to you. If I make those kind of predictions, how do you judge whether I'm good or not? Because I could always just say, like if I say it's a 70% chance of rain tomorrow and it rains, I can say, yep, told you. And if it doesn't rain, I could say, yep, told you. So that's not really just, right? So there's a family of loss functions that you can use to judge the weatherman, right? They've got a name, they're called proper losses. It turns out that every proper loss can be decomposed into these cost-sensitive misclassification losses. They end up being primitives, right? They're like think of a basis function, if you like, right? So they've got this very nice property, right? And that is in the back of our mind that allows us to do this. So that reason, along with the fact that it does allow you to do the trade-off between false positives and false negatives, is good, right? So, long answer, but it's a good question. Anyway, so that's the key claim, and I do have a proof here, and as I said, I'm not going to try and walk you through that in class. You can go and read that. I believe it's true. You can check it. Tell me if you find a mistake, right? But it's just substituting in and checking. And we can do a similar thing for MD, right? Remember, MD is where we just go and take the ratio. There's a similar relationship there. In this case, you actually do get inequality, right? So the first line there, MD of F is actually equal to this cost-sensitive balanced loss in that fashion. It just turns out to be that way. And then, of course, that implies this. So again, we can use it for the constraint. Because what we'll want to do, right? So if we have this approximate measure of fairness, so I didn't say this before, so I said you can't get perfection, we have some approximate measure of fairness, and then you might say, okay, we know we can't be perfectly fair, but I want to have a fairness deviation of no more than 0.1, right? I can actually go and say, I could have it as a constraint, and then I could go and say, under that constraint, give me the best prediction possible. That's one of the ways that we can look at this problem. So that's why we would like to be able to cast our fairness constraint in terms of the language of risk functionals, because they're things that we can glue together with our standard way of doing things. So with all of that, it turns out, so the heading of the slide covers the key thing. Reducing these two particular types of fair machine learning to a constrained, cost-sensitive learning problem. So that's a reduction that we've achieved. So reductions are a standard trick in computer science. You're given this big new problem, you show you can reduce it to this other problem. Cost-sensitive misclassification loss problems, they're old hat. That's something that we understand. What we show is that if we measure approximate fairness in the way that I described, we can formally reduce the problem of predict as well as you can, subject to this fairness constraint, in terms of these cost-sensitive misclassification losses. And the slightly weird thing about this problem is you end up with this minus sign. You have a positive lambda here. I don't think I say that lambda should be positive, but essentially what you want to do is you want to be able to predict the y's well and you want to predict the sensitive attribute poorly. That's what the trade-off ends up being. And you're using the same F in both cases. This is the crucial thing. So with that, right, once we found that we can actually formulate the fairness aware problem in this fashion in terms of risk functionals, we can actually work out the theoretical optimum solution. So I'm realizing I'm a little slow on time here, so I'm going to rely on you looking at some of these slides yourself, and I think I will just get to the solution and describe some features of it, because I think it does give you some insight. There's some notation you're going to have to absorb. There's an argument that I give here, but the key takeaway is here in blue. So this is, I definitely want you to remember. So remember about 5 or 6 slides ago, I gave you the formula for the optimal classifier for a cost-sensitive misclassification loss, right? And it's essentially that eta of x had to be greater than c, right? If that was true, you predict 1. If it's not, you predict 0. When you go and look at this and you digest the formulas, what it says is that you apply a constant threshold to the these class conditional probabilities for each value of the sensitive feature. So you have this revised notion, so eta is now conditioned on both x and s, so this thing means the probability that y equals 1 given the value of x and s, and you essentially do the same thing as you did before, but just with this more complicated object. It's quite satisfying, right? That you can actually work out the optimal thing to do. And you can do it for both measures of approximate fairness that we have, and it's a similar argument. I mean, I know this all looks daunting, but I don't know how to make it simpler. And the fact is, we do actually work out the optimal thing to do. And I'll tell you why, right? We're getting to why would you bother to do this? It seems like a lot of maths to go to, for something that you can't actually compute in practice. Right, so what, right? So the fact that you can actually do this is a big surprise. We were not expecting that. Normally you can't compute the Bayes optimal classifier. We made the problem simple enough so that you could just do it. It's very satisfying. It's a correction of the fairness unaware Bayes optimal. So we have this trade-off parameter lambda. If you crank through the maths that I showed you and you let lambda go to 0, we recover the classical case. You crank lambda up, you see that there's a larger and larger departure from what you would have done if you took no account of the sensitive attributes. The exact form that you get depends upon your DP or EO. We would have expected that. I told you these choices matter. The impossibility results suggested that they matter. The exact form, it does depend in a satisfying way on these knobs. You'll have to stare at the formulas to, well, I don't know, satisfying to me. I don't know how satisfying you're going to find it, but what do I mean by satisfying? It's understandable. You can see, yeah, this makes sense. If I crank this up, it does such and such. And it does actually suggest an obvious plug-in estimator. So this is a standard trick in statistics. You assume full access to the distribution, you calculate the ideal thing that you would do, and then you replace the true distribution by samples and just plug it into your formulas, right? And that would actually work pretty well. But it's even better, right? With this, we can do something that you cannot possibly do if you just took an algorithmic approach to this, because now we can actually quantify the trade-offs, like the question that you asked before. So trade-offs are essential, right? So there's this thing called the engineer's tripod: better, cheaper, faster, pick any two, right? You want to build some machine, you can either be better and cheaper or better and faster, but they conflict, and it's usually more complicated than just 3. And likewise in economics, designing economic systems, there's always trade-offs, right, between social equity of different sorts. So there's many sorts of trade-offs that you get in machine learning. There's an interesting example here I will let you read, that I won't point to. What we can do now with what I've talked about is we can actually compute the Pareto frontier. So we can compute, we say, we're not restricted to finite samples. It's not like we've got a model class. We're not restricted by the amount of computation that we've got. If we assume the optimal situation, infinite data, infinite compute, we do everything exactly and perfectly, there's still a trade-off and we can compute that. And that's kind of interesting. And it ends up having an interesting interpretation. So you end up with this, okay, this complicated formula. I know you can't absorb all of this in the short amount of time I'm giving you, but I think you should be able to study these slides afterwards and understand the basic gist of it. And there's a nice interpretation to it. And this interpretation then allows you to answer interesting questions like the following. It turns out, it's just a fact now, that sometimes you'll be able to demand, you'll have your optimal solution, ignoring fairness. You'll come along and you'll say, I demand a high level of fairness, and nothing will change. You'll be able to do just as well as you did before. That can happen, and what this formula does is it will explain what circumstances that does occur. But sometimes it's a tougher situation. You'll find that you've got your optimal solution ignoring fairness, and now for every percentage point increase in the amount of fairness that you achieve, essentially you get a percentage decrease in your performance. It's very easy intuitively to understand how this could occur. Just think of the situation that your sensitive attribute S was equal to the label Y. Now it's a kind of absurd one, right? But I'll give you a toy example. I want to predict the probability that any of you will have a baby, right? And it turns out that that's really highly correlated with your sex, right? So, right, there's a one-to-one correspondence. So that's, of course, a silly problem, but there will be situations in the world where the sensitive attribute is actually correlated with the thing that you're trying to do. Now, there's a whole stack of questions behind that. We're assuming that there's some distribution. We might just be talking about what happened in the past. But here we had a limited scope, right? All I was trying to do today was to look at what's the simplest way you can formulate a fair machine learning problem, and can we understand it rather than just saying, oh, I'll come up with an algorithm and I'll try it out and it kind of works. Here we can actually say, we work out the best possible algorithm that you can do and understand what the trade-offs are. So see if you can make sense of the text on the slide when you read it. I have a question here which I've kind of talked a little bit about the best and the worst pairs, right? The best would be where you can get fairness for free, and the worst will be where you've got a very large price of fairness. And in the paper, we actually did some toy examples, right? I mean, they were sort of synthetic examples where you can actually plot the trade-off that you get, right? Just to show that in principle it's done. The key thing is that this does depend upon it does depend upon the data. Now, some conclusions from this. I'm almost done. I think I've only got one more slide. The fact that there is a trade-off tells us something quite important. It means we can't just look at the fairness, right? If we just said, oh, well, we have these systems, we've just got to go and put a fairness patch on them, what this says is that when you do that, you will pay a price. It's like most vexed things. You know, I'd like to make my car emit less CO2. Well, how am I going to do that? It's going to cost. You know, we have to use lighter materials, which costs more, or have a different kind of engine, which will cost more, or what have you. So we have to grapple at the same time with the performance and the fairness. So that's a key takeaway from today. Another key point. This trade-off, because of the way I analyze this, it's a property of the data, not an algorithm. Now, this is quite important. That picture I put up on the first slide of the ProPublica article about the recidivism risk prediction, when you go and read that, and you read a lot of the literature that I ask you to do a Google search for, you'll see people talking about biased algorithms, right? It's a very common phrase. The problem is biased algorithms. What we did here, there was no algorithm, right? We worked with the optimal predictor and there's still a trade-off, right? So it's like you have to suck that up. That's just the way the world is. It's even if you have the best possible algorithm, there will be a trade-off here. So you can't, this is not a problem that you can solve by just being smarter about your algorithm. You have to think rather more broadly. The fact that it depends upon the data doesn't mean you just have to say, oh, well, that's just the way it is, we can't do better, because you could change the data, right? The data depends upon other things. You now have to start thinking, well, maybe the reason why the data says, let's say, women default on their loans more than men is because they've never been given the opportunity. So if we give them the opportunity, they might do well. It gets more complicated, but now we've changed the rules of the game. I've just illustrated one of the moves that we'll make a lot in this course. We take away of framing the problem, we go and look at it, we see what the implications are, but then we realize that the trick is not to try and solve the problem better, but to ask a different question. So I'm done. So what did we cover today? I'm sorry this went slightly over time. We saw two basic definitions of fairness used in machine learning, the role of conditional independence in these and some of the headaches. Actually, I didn't really talk about the headaches of that, I will next lecture. The distinction between perfect and approximate fairness. A surprising amount of the literature just focuses upon the perfect case. This idea of approximate fairness, I think, was new in the paper I did with Aditya. I'm not sure, but as far as we knew, that was new. The notion of a fairness trade-off, which I think is really important. Trade-offs really matter for engineering, right? I mean, if you can get to the essence of the trade-off, then you really understood your problem. You haven't necessarily solved it to everyone's satisfaction, but at least you know what you're facing. The abstraction of these particular measures of fairness as they are stated in the literature in terms of these conditional independencies, abstracting them as expected risk functionals, that's a fair bit of work in the paper, but the payoff is that it allows us to then go and formulate the problem in a way that we can then understand it. We then see, it's a constrained optimization problem. We do Lagrange multipliers, we do all of our standard tricks in machine learning, we can then go and understand it. That's what allows us to compute the Pareto frontier. And as I said, I think we achieve better understanding by abstracting away from the algorithms. So thank you very much. See you next week.